going to talk about 4 different ways to test one proportion, but they're all variations on the same idea. So the first one is a simulation-based test. This is the first one that we learned, and one really big benefit of this is that this is a very flexible approach. You're allowed to use whatever statistic you want. Your null distribution is going to be based on a simulation, so coins, spinners, something like that, but you can do it for any sample size. So you don't have to check any validity conditions first. As long as your simulation matches your scenario, then you're good to go. The second test that you learned was called a one proportion z-test. So here, instead of using a simulation to get the distribution, you're using the normal distribution. So sometimes a one proportion z-test, we call that a normal approximation, because you're using the normal distribution to approximate what would happen if the simulation were actually done. It's called a one proportion z-test because historically the statistic that you would use for this is the z-statistic, or what our book calls a standardized statistic. And the reason is because a standardized z-statistic has a really nice theory-based null distribution. Specifically, it has a standard normal distribution. Standard normal means that the mean is 0 and the standard deviation is 1. So this is really great because then when you see a z-statistic of, say, 3.5, you know right away, without knowing anything else about the context, that this is strong evidence. So that standardization is a big benefit. Just remember that you have to check the validity conditions to decide if this is valid. You're going to look at the expected number of successes and failures. N times the value from the null hypothesis needs to be at least 10, and n times 1 minus the value from the null hypothesis also needs to be at least 10. One downside of a one proportion z-test, and this will make me mad every single year, is that JUMP doesn't do a one proportion z-test. I have no idea why. It makes no earthly sense to me, but it doesn't. So really the only way that we can do that is with the applets. The third test that we're going to talk about is called an exact binomial test. Historically, usually people would use just the number of successes here. And it has, for its null distribution, this really fancy formula. In a later video, I'll show you where that formula comes from. But this is another one where you don't have to check any validity conditions. It works for any sample size. So that's great. Also, JUMP does do a binomial test. It only does a one-sided one for some reason, but you can do both one and two-sided in the applet. And the last test that we're going to be talking about can be used in even more scenarios than the other tests that we've learned so far, because a chi-squared goodness of fit test works even if the variable is not binary. So this is still for categorical data, but it doesn't have to be just success failure. You can have data that's not binary, so 3 separate categories, and you care about all 3 categories. You don't want to lump any of them together. That's a chi-squared goodness of fit test. It has its own special statistic called the chi-squared statistic that we'll talk about in a later video. It also has its own theoretical distribution. So sort of like you can use a normal approximation, you can use a chi-squared distribution to approximate the distribution of chi-squared statistics as long as you have certain validity conditions that are met. Chi-squared tests are available in JUMP, and that's especially nice because it sort of gives us a workaround to get a z-test. And the reason for that is that the chi-squared statistic and the z-statistic are related. The chi-squared statistic is actually just the z-statistic squared if the variable is binary. So remember, chi-squared tests can be used for non-binary categorical variables. Z-test is only for binary, but in the case where the variable is binary, both tests provide the same information. They'll ultimately lead to the same p-value. The only catch is that chi-squared tests are always two-sided. So if you want to get a one-sided p-value, so like let's say that you were using this as a way to get to a z-test, and you wanted to get a one-sided p-value for your z-test, then you would have to divide the p-value by 2. So take the p-value that you're getting from the chi-squared test and divide it by 2. And the reason this works is because if you think about a z-test, it's using a normal distribution. The normal distribution is symmetric. So if you look at a two-sided test and you want to get to a one-sided p-value, you just divide that p-value by 2. So even though the purpose of all 4 of these tests is basically the same, there's some limitations for when you can use each one based on the sample size and the type of data and 1 versus 2-sided tests. So there'll be some opportunities to practice with these details.